Now, we will discuss about the characteristics Mach number that we had earlier defined and express the spatial energy equation that we had derived. If you look at, that is basically a square divided by gamma minus 1 plus v square divided by 2 is equal to gamma plus 1 divided by 2 gamma minus 1 a star square. What it indicates, as I told earlier, that it indicates that this what you call characteristics speed of sound remain constant along a streamline, and we need to express this equation in terms of characteristics Mach number, right. So, what we will do? We will just divide this expression A 2 by v square, and then naturally what will happen? This become 1, and we will divide by v square here, right, both the LHS and RHS I am doing. So, what I will get here? I will get in this place 1 over Mach number square. Similarly, what I will be getting here? 1 over Mach star square. So, if I will do that, I will get, I mean already I have done A by v square. So, I will get 1 over m square plus half is equal to gamma plus 1 divided by 2 gamma minus 1 over m star whole square, right. Now, I need to express this in terms of like in terms of m star, right. So, for that let us, what I will do? I will just take this over at the other side, that is I can write down this term as 1 over m square into gamma minus 1 is equal to gamma plus 1 2 gamma minus 1 over m square minus 1 by 2. So, I will just subtract this thing. What I will get in the denominator 2 gamma minus 1 m star square and gamma plus 1 minus m star square gamma minus 1, right. What I am doing? I mean very simple, I am doing this thing, and then I need to express this m, because m square in terms of m star. What I will do? I can just cancel this term, right. Can I not? I can cancel. So, then it will be and what I will do? This portion I will take to this side, and then 2 m star square I can take to this side, and this term I will take to this side, right. So, what I will get then? M square is equal to 2 divided by gamma plus 1 m star square minus gamma minus 1. I can get very easily, right. That means, what is saying? That Mach number, local Mach number can be related to the characteristics Mach number. Of course, what you can say that this Mach number, local Mach number is a function of characteristics Mach number and gamma, right. That is he is saying. What is saying? Is saying m is a function of gamma and m star. This expression says that to me, is not it? Am I right? And we can express this just other way around, that is characteristics Mach number in terms of local Mach number, right. So, that is equation 2 can be rewritten as, I mean this is little algebra, that is what I am doing. This is 2 by m square is equal to gamma plus 1 divided by m star square minus gamma minus 1. I have taken this term basically over here and this over here, right. Then what is coming there? Like basically m star square in the denominator, and then gamma plus 1 minus m star square gamma minus 1. If I divide by this, both the numerator and denominator by m star square, I can get very easily that m star square is equal to gamma plus 1 m square 2 plus gamma minus 1 m square, right. And let us look at how this characteristics Mach number is dependent on the local Mach number. If local Mach number is equal to 1, what will happen to the characteristics Mach number? It will be also equal to 1, is it so? Right? Definitely yes, because this will be 1 and this is 1 and gamma minus 1 plus 2 became gamma plus 1, that became 1. If it is Mach number less than 1, local Mach number, what happens to the characteristics Mach number? It will be also less than 1, right, yes or no. Similarly, if it is local Mach number greater than the 1, that is your supersonic flow, then the characteristics Mach number also will be greater than 1 for a particular of course gamma, right. We are considering let us say gamma is equal to 1.4 and then looking at. But if the Mach number tending towards infinity or it is a very big local Mach number, right, what will happen then? Huh? It will be dependent on gamma plus 1 and gamma minus 1 root over, that means gamma plus 1 divided by gamma minus 1 root over. How I am getting this? It is in the limit when m is tending towards infinity. When you talk about limit, then how you will get this? You will have to use L'Hospital's rule. So, these I am leaving as an assignment to you and you will have to do it and let me know whether you are getting or not. That means, what is saying? This simple expression says that it is almost similar to the characteristics characteristics Mach number is similar to the local Mach number, but when the Mach number is tending towards infinity, it is not, it is a some constant value, right. Okay. So, that is this expression sometimes we will be using this characteristic Mach number, particularly when we are dealing with what you call normal shock and maybe something Rayleigh flow kind of things, but I will be using Rayleigh flow, given assignment how you can use it for a normal shock, right. So, coming to that, let us now look at what are the attributes of compressible flow. Just to summarize, the density of flow cannot be assumed to be constant, what we do generally for incompressible flow, right. We always say that incompressible flow means density will not be changing, right. But as I told you that you cannot have that, it is a myth, but practical purposes we use it, and information propagates in all direction depending on its local Mach number. We have already discussed and we will be using this concept to talk about the shock formations and other things. So, regions of mixed flow like kind of things subsonic, transonic, supersonic can be present, right. Particularly in transonic, both the subsonic and supersonic flow will be there, right, we have seen. And Bernoulli's equation, what we generally use for incompressible flow like P plus half rho V square without any contribution from the what you call this height or potential energy is remain constant, that cannot be applied for compressible flow, which we have already derived an equivalent for the compressible flow from the energy equation. And the last but not the least, that is the coupling between kinetic energy and internal energy cannot be ignored. What is the meaning of it? If you look at your energy equation, we always say that H plus V square divided by 2 is constant, that is of course for along a streamline, right. Here if it is compressible flow, then what happens, the kinetic energy will be converted into the enthalpy. when you talk about enthalpy consists of internal energy and PV, PV is your flow work, right. So, therefore, this energy will be converted into kinetic energy, will be converted into the internal energy, and it is quite this thing. So, it cannot be really ignored, that which we ignore in case of incompressible flow, because the change is very minimum, right. So, we have looked at the basics of the compressible flow, right, and today we will start this lecture 10 with a statement from Richard P. Feynman, who is my favorite. He says that, but I do not have to know an answer for asking a question. Last time I talked about question. I do not feel frightened by not knowing the things, by being lost in the mysterious universe within any purpose, which is the way it really is. So far as I can tell, it does not frighten me. What he is saying? He is saying that he is not really frightened by for asking a question, right, because unless otherwise you ask a question, you cannot do really any meaningful activities in the life, not only in the science and technology, but also in the life. Therefore, it is very important to ask question, and if you look at what is the profound statement he has given. Therefore, I would urge you people to look at what is the importance of life and how you can contribute and how you can do for the science and technology. So, with this thought process we can start this lecture, and as we do recall the things in the beginning, what we have looked at in the last lecture about the basic concepts of the compressible flow, starting from the stagnation point, the stagnation properties, then you look at specialized energy equation, then you look at characteristics Mach number, how it can be couched in the energy equations or express the specialized energy equation in terms of the characteristics Mach number, and we have related characteristics Mach number to the local Mach numbers, and also right. Now, we will look at basically quasi one dimensional flow. Why you are looking at quasi one dimensional flow? Because we will be dealing with the analyzing, basically we will be analyzing the propulsive ducts, where flow is likely to be one dimensional, not all the cases, but however, in case of a nozzle or in case of a diffuser, we can happily consider the flow to be one dimensional, of course, for the simplicity, provided there is no flow separations and other things are occurring, right. And I have already explained you what do you mean by quasi one dimensional flow. Let us consider there is a duct which is diverging in nature, right, and through which the fluid is coming with a uniform velocity and having the velocity v, and of course, the pressure P here and density is here, and the cross sectional area is A, we can consider, and it is the flow is going, and then of course, we need to analyze this what is happening here. And if you look at whether we can take this flow in this duct as a quasi one dimensional or not. If you look at, the flow can be three dimensional in nature. For example, if I take x along the axial direction and r along the radial direction, and theta is in the theta direction. So, r theta z coordinate system, because in propulsive devices we use the duct, right, duct with a circular cross section, right. So, therefore, what will be the flow in this case? Even if you are having a uniform velocity profile in this region, but still can I call it as a flow to be one dimensional? And because of flow is if it is a circular cross section, I can consider the flow to be symmetric along the theta direction, right. So, therefore, it will be two dimensional, right. Then there will be flow along the x direction along the radial direction. But is it really we can consider the flow to be one dimensional, provided the rate of change of this area is very, very small. That means, this rate of change of area what I have shown here, if it is small and then the change in the velocity along the x direction is more as compared to the change in the r direction, right. If you look at this is my r direction and this is my x direction. So, in r direction will be very, very small, then we can call it as a quasi one dimensional flow. And in this, let us say there will be work interaction in case of your compressor and turbine, there will be work interaction, but in case of your nozzle and air intake, there will not be any work interaction, because is having no rotary motions kind of thing. We just enhance the flow in a nozzle and decrease the flow in an air intake, right. So, therefore, we are now talking about generalized one. There will be some heat interaction, that means in depending upon kind of propulsive duct you are talking about. So, we need to analyze generalize equation will be deriving, and we will make some assumptions. What are those assumptions? Which is I have already told you, that is the flow will be steady and quasi one dimensional flow, and then we are considering the flow to be inviscid. But however, I have kept here the shear stress on the wall just to make it more generalized, because we will be using this equation later on, and we will make some assumption of inviscid flow as you go along, and there is no body forces, and the gas can be considered to be an ideal, and that means we need to use the perfect gas equation, and constant thermodynamical properties will be using. And when the properties remain constant, that means it is not changing when it is flow is taking place. The properties, for example, Cp, Cv, although it is a function of temperature, we are not considering to be function of temperature, that means Cp will be remaining constant. As you go along, we will use some variation variable in propulsive ducts, we will see in the cycle analysis what changes it can make. And when you do that, that is basically what you are doing, you are using calorically perfect gas. So, now we need to analyze this. For that, we will take this control volume what I have shown here as the dashed line, right, and apply the conservation of mass, momentum and energy equation, and then we need to invoke also the equation of state for a perfect calorifically perfect gas, then we will solve that. Let us consider now the for this control volume continuity equation. For a steady flow, there won't be any steady term. So, that became rho V n dA is equal to 0. In this case, if you want to look at what it will be, if we just look at this point, because this is the inlet to the control volume and the flow is going out of this control volume. So, if I look at here, it will be rho V A, that is rho V A, right, rho V A minus rho plus d rho, right. In this case, rho plus d rho at the exit of your control volume. Of course, this is cancelling out, I can just to show that it is a change in density. Therefore, I have taken, right, into V plus d V into what will be area in case of A plus d A, because this is what? This is a quasi one dimensional flow. When I talk about quasi one dimensional flow, area is a function of x here, right, for quasi 1D flow. But for a 1D flow, what will be? Area is not a function of, rather area is constant, right, is like a pipe. Okay. So, therefore, A plus d A comes into play is equal to 0. If I simplify this thing, neglecting the higher order terms, right, and simplifying further, I can get an expression which says that d rho by rho plus d A by A plus d V by V is equal to 0, right. So, that means, if you want to see that what really says, if I say that means it is saying, right, it will be see what is the meaning of this. If you look at this thing, this basically mass flow rate, that means mass flow rate entering here and mass flow rate exiting out of the control volume. This is your mass flow rate. If you look at mass exit and mass dot in is equal to 0. I mean, we have already talked about it, d m by d t is equal to m dot E minus m dot I, right, you can say that. So, you can get this expression, and let us invoke the momentum equation for a steady quasi one dimensional flow, that is rho v v dot n into d A is equal to summation of forces like x, right. So, if you look at what are those forces, will be, one will be pressure forces, right. Other we are considering the friction, the tau w, without considering the boundary layer effects and that thing, right. It is a little other way around. So, let us look at what is these things. In this portion, what it would be? It will be rho v square A minus rho plus d rho v plus d v whole square A plus d v d A summation of f x, right. Can I not get this left hand side of this equation I am doing, right. So, and you can, and then we will have to substitute these things, that is, as I told you, pressure, and when you talk about this pressure, how you will do that? Can I take this control volume? For example, if I take this control volume here, what will be pressure acting over in this surface? What will be pressure? P. And what is the area? P A will be P A. That means, the force acting on this surface will be P A. What is the force acting over here? P plus d P into A plus d A, right. Keep in mind that this thing is in equilibrium, therefore, it will be opposite, right. But is there any force which will be acting on this surface? Certainly yes, right. That force we can take as a P plus d P by 2 into what area it will be? Huh? Certainly no, this will be d A. What is d A? d A, if you look at, it is this area is d A, right. So, if you do that, and what is the force it is acting here? Tau w, into C, if I take this circumference into delta x, right, delta x is this. So, that is the force is acting, which is opposite to this x, therefore, the pressure force will be negative, and so also the frictional force or the, right. So, when you do this thing, you will get an expression, you will simplify higher order term you neglect, you will get rho v A d v is equal to minus A d p plus tau w C d x. As I told you that C is basically circumference of this control volume. Of course, which control circumference you will take? You will take the average, right. Circumference will be changing here, you will be changing there, right. So, we take that and what I will do? I will divide this equation by A and dx. Similarly, if I divide this equation A by dx, what I will get? See, this A will cancel it out, this become rho v dv by dx is equal to A cancel it out, dp by dx minus dv by dx minus tau w c by A, right. So, if I will do that, momentum equation becomes rho v dv by dx is equal to minus dp by dx plus tau w c divided by A. Keep in mind that in the whole is bracket minus, right, because it is in opposite direction, right. The frictional force is always opposite direction to the flow, right. And now, we will invoke the energy conservation principle, and in the similar way we can derive it. Rho V A d h plus V d v is equal to d q minus d w. What is this term here? This is your mass flow rate, which is remaining constant, although it is a diverging duct in this example, but mass remains constant, right, because it is a steady flow, am I right. So, I can divide this both the left hand side and the right hand side by this one, right. So, that this will cancel it out. What I will get then? I will get d h plus V d v is equal to d q minus d w. What is this thing? This basically is heat per unit mass, the heat interaction per unit mass flow rate or mass, and this is the work interaction per unit mass, right. So, now we will have to invoke this equation of state for an ideal gas, which we already know that P is equal to rho R T. Keep in mind that this R is specific gas constant. That means, this is equal to R u by molecular weight, right. Universal gas constant divided by molecular gas is a specific gas constant, right. That means, this specific gas constant will be dependent on the kind of fluid you are handling. If it is air, it will be 287, right. Some number I am just telling, but it will be different for different gases. The momentum equation for an inviscid flow, what it becomes? This will be 0. So, when it is 0, that is rho v dv plus dp is equal to 0, because you know it is a dx. So, rho v dv is equal to, if I take to this side, it become is equal to 0. And combining this equation 5 with the 1, what is that equation 1? We have that is nothing but your continuity equation. We state that d rho by rho plus d a by a plus d v by v is equal to 0. What we will do now? We will basically substitute over here. That means, if I say this is d v by v, what I will do? I will just divide here v and I will become v square, right, because I am putting v here and then I can do that. In place of dv by v, what I will do? I will put minus d rho by rho and minus d a by a in this place, right. In this place, I will be using these terms, keeping in mind that with a minus sign. When I will do that, what I will get? I will get dp plus rho v square minus d rho by rho minus d a by a, and we know that we can relate this d rho with the dp. How? From the definition of speed of sound, that is nothing but your A square is equal to dP by rho d rho, and so d rho by rho becomes dP A square into rho, right. So, I will substitute over here these values, right. So, if you look at, if I take this out here, what I will say, rho can be cancel it out, and V square A square, if you look at what became, this is nothing but your Mach number square, right. So, then this term becomes, if you look at dP, if I take it out, it will be 1 minus m square, right. We will do that. So, I have already talked about this equation. So, as I told you earlier that if I take this term outside here, and rho will cancel it out, and it becomes basically V square by A square is nothing but your V square by A square is nothing but your m square. So, dP, if I take it out, it became 1 minus m square is equal to rho V square dA by A. That means, this expression is relating not only the pressure difference and Mach number, but also the change in area, right. So, let us what you call simplify this further. And as I told you earlier that equation 7 depicts the effect of Mach number on the flow in a variable area duct, right, because if you look at the area is changing and Mach number is there, of course, for a certain pressure gradient, how it will be related, it is being depicted in equation 7. By using equation 5 in equation 7, what is that equation 5? It is nothing but your rho V dV plus dP is equal to 0, right. So, we will substitute here in place of dP, what I will do, I will put minus rho V dV, right. In place of dP, what I will do, I can put it as a minus rho V dV. I mean, if I do it here like minus rho V dV 1 minus m square is equal to rho V square dA by A. So, rho cancel it out, rho, and V cancel it out, V. So, if I divide it by this V here, so what it comes? It comes dV by V 1 minus m square is equal to dA by A. In other words, I can write down as dA by A is equal to m square minus 1 dV by V. So, yeah, okay, fine. So, we will arrive at dA by A is equal to m square minus 1 dV by V is, I mean, this is the relationship, and if you look at this relationship, what is saying? It is relating the change in area with the change in the velocity. If m is less than 1, what will happen? If m is less than 1, and that means, if I want to accelerate the flow, I will have to use a decrease in area, what you can see here. When there is a decrease in area, what happens? The velocity increases, as I told, and also pressure decreases. Now, if the m is greater than 1, what happens? Like this term become higher, that means, it becomes positive, right. This became positive if m is greater than 1, and if it is positive, that means, area has to what you call increase for increasing the velocity, right. That means, V 2 should be greater than V 1, or V exit area should be greater than inlet area. Therefore, I will get a acceleration. Of course, here again the pressure decreases and velocity increases, but if I combine this together, what I will get? I will get a duct which will be basically make the flow to be supersonic, right. How it is? Because if you look at m, when m is equal to 0, when m is equal to 1, what it would be? It will be dA by A is equal to 0, right. That means, there will not be change in area. It can be of course maximum or it can be minimum, but generally maximum will not give you physical results, whereas the minimum one will give you the physical. Here that means, the Mach number will be 1 here in the throat, where if you look at this area is the minimum, as it is converging and again diverging, converging and it is diverging. So, therefore, the throat, this is known as throat, right, and where Mach number will be equal to 1. So, let us consider the other way around, that is basically we want to decelerate the flow. If you want to decelerate the flow, then what you will have to do? Basically decelerating flow means V2 should be less than V1. For example, if I take this is my 1 and this is my 2, that means my flow should be for deceleration of the flow, V2 should be less than V1, right. That means, what will be that? dV will be negative, right. So, what we have looked at, the expression is we have looked at, right. That means, this if this is negative, right, this term is negative, we want to have, what we will have to do? If m is less than 1, that means this is become negative, right. So, negative negative become positive. So, that means area should be greater, that means A2 should be greater than A1 if m is less than 1, right. That is the what is being shown here. That means, if it is divergent duct, the velocity will decrease and pressure of course increases. Similarly, if m is greater than 1, what we will get? We want to decrease this, because this term is negative and this is positive. Therefore, area should be less than A1, right. So, then we can decelerate. So, if you look at, this is basically the supersonic diffuser, where the flow is subsonic at the entrance and it goes decreases because the flow is supersonic, and then it decreases further after passing through the throat, and this is being used in your what you call air intake kind of thing, which we will be discussing a little later on when you are discussing about cycle analysis. Now, we look at area Mach number relationship. Let us consider a convergent divergent duct, which I have shown is attached to a reservoir. Reservoir means what? That means, here velocity will be almost equal to 0. That means, it is a very larger area, right. And if velocity is almost 0, then what will be the properties? Properties will be total or the stagnation properties, like Pt, Tt and rho t kind of things, right, total temperature. And we this is our throat area, where the flow is likely to be sonic condition. Therefore, I am using star here, right. And of course, any area it can be Mach number will be dependent depending on what really for it is designed. So, also the velocity. What we will do? We will just take the mass flow rate because here we are using a steady flow. So, therefore, mass will be remaining constant in each cross section, right. So, I can take m dot is equal to rho V A is equal to rho star V star A star. What is the meaning of this? This is basically at the throat. That means, whatever mass flow is coming over here, it will be same as that of at this point. Is it agreeable? So, from the continuity equation, we can derive an expression for mass flux. Mass flux means what? Mass flux means mass flow rate per unit area is nothing but a rho V. And what is this V? V we can express velocity, right. V is the velocity of the fluid at particular cross section in the duct, convergent divergent duct. It can be anywhere, this generally we are talking about, and this velocity can be expressed in terms of Mach number, because by definition we know Mach number is equal to V divided by A. So, this is m into A, and A is nothing but your root over gamma R T. So, in place of this, we need to now relate to the reservoir properties. What are the reservoir properties? Those are total temperature, pressure, density, like that, right. So, what I will do then? We have already derived expression for the temperature ratio, that means rho T divided by rho is equal to 1 plus gamma minus 1 divided by 2 m square whole power to the 1 minus gamma minus 1. We have already derived, right. You are not getting, I think let me write down here, rho T by rho is equal to 1 plus gamma minus 1 m square power to the 1 minus gamma minus 1. So, in place of rho, what I will do? I will write down the rho T by 1 plus gamma minus 1 divided by 2 m square power to the 1 minus gamma minus 1, and m remains same here, and in place of T, you know, this is the T here, I will express this T, that is the static temperature, right, with respect to the total temperature corresponding to the reservoir in this example, that is gamma R T divided by 1 plus gamma minus 1 divided by 2 m square. Okay. So, what we will do now? I will, instead of rho T, you know, I can use equation of state for a perfect gas, and then express in terms of what you call pressure. So, instead of that, I can write down P T by rho T. In place of rho T, I will be writing R P T divided by R T, and of course, same thing remains, and we would need to simplify, right. If you look at, I can simplify very easily, you know, which may I can do here or I can do later on. Okay. So, and if you look at this term, and this term is similar in nature, right. Okay. So, we can club this together, because this says 1 plus gamma minus 1 divided to m square power to the 1 by 2, and here it is 1 by gamma minus 1, the same term. So, we will be trying to club it. So, if you look at, I can write down 1 divided by 1 plus gamma minus 1 2 m square, right, power to the 1 minus gamma minus 1 plus 1 plus half. What will be if I take this term gamma 1 plus 1 by 2, what it would be? It will be 2 gamma minus 1 2 plus gamma minus 1 is equal to gamma plus 1 into 2 gamma minus 1. That means, in place of this term, I can write down this, right, and keep in mind that this, if I will cancel it out, this became root, that means, this will go away, right. So, what is saying, this mass flux ratio will be function of P T, function of Mach number, and then gamma, which will little bit simplify in the next and see that. So, by rearranging this, I can get this m dot root over T A P T, what I am calling it as that mass flux parameter, right, MFP, which is not seen here. So, is equal to root over gamma root over r, because T I have taken m 1 over 1 plus gamma minus 1 divided 2 m square power to the gamma plus 1 divided by 2 into gamma minus 1. What it says that this mass flux parameter is a function of Mach number and gamma, right. That means, it is a function of flow velocity, right. Mach number we use it for convenience, right, and gamma is the Cp by Cv. That means, it is dependent on the kind of fluid being used. So, as I told you, I am saying this term as a mass flow parameter. So, this if I plot this expression, for gamma is equal to 1.4, what I will see? I will see this mass flow rate with Mach number, it increases, it increases and reach a certain value, then it decreases, right. That means, if I am increasing this mass flow rate, then it will be goes on increasing, right, and then decreases. And these peak values occurs at Mach number is equal to 1, right. These peak values occurs as a, of course, this you can call it as a subsonic flow, it will be goes on increasing, right, mass flow parameters and decreases. What is the implication of this? We will be discussing it little later on. What is the implication? Of course, it is increasing and decreasing. So, what? You can just immediately see that what is happening to this mass flow rate. It will be, dependent on what? Dependent on pressure, total temperatures, kind of thing. So, we will be looking at little later on. So, just to talk about it, like that for sonic flow m is equal to 1, what we will get? Equation 9 becomes m f p max, that is the maximum flow rate, which is corresponding to m equal to 1 Mach number. It becomes like what I will do? I will put m is equal to 1 in this equation, m is equal to 1, that means, this become 1 term, right. And if it is 1, what it becomes? This will be 2 plus gamma minus 1, that becomes gamma plus 2. So, and 2 will go to the numerator. So, that becomes 2 divided by gamma plus 1, right, and m here is equal to 1. So, from equation 9 I can get this expression very easily. That means, if I one equation, this is general, this equation 9 is for general one, right, and this is for the only sonic flow, where Mach number is equal to 1. If I divide this expression, divide this equation 1 by equation 9, what I will get? I will get an expression A by A star ratio, right, is equal to 1 over m 2 divided by gamma plus 1 into 1 plus gamma minus 1 divided by 2 m square, of course, the whole here bracket to the gamma plus 1 divided by 2 gamma minus, right. How I am getting that? Because if you look at this equation 10 is divided by equation 9, that means, m f maximum divided by m f I am doing. So, if I will do this thing, this mass flow rate will be cancelling out, right, okay, fine. And then this A by and root T will be cancelling out, P T will be cancelling out, what you will get? A by A star in the left hand side, right, and in the right hand side what you will get? You will get 2 by gamma plus 1 this term, right, and these gamma root over gamma and r will be cancelling out with this equation 9. So, and then this term will be coming just what to call the the denominator, and as it is 1 over this, that became 1 plus gamma minus 1 divided by 2 m square. So, what it indicates, this area ratio is a function of what? Is a function of Mach number and gamma, right, and this is known as area Mach number relationship, and what it indicates is the local Mach number is dependent on the local area with respect to sonic throat area, that means A star. If you look at this is your sonic throat area, right. So, what we will do? We will look at this variation, that expression what I have talked about here, and let us see how it is varying with respect to the Mach number, and when we are talking about it, we will be looking at T by T T also and P by P T, because the P is the local pressure or the static pressure and P T is the reservoir pressure or the total pressure. The curves will be looking like this, right, A by A star and Mach number I have plotted here. If you look at this curve, shows for the solid line, shows for the gamma 1.4 and gamma 1.3 for the dashed line, and if you look at this Mach number is equal to 1, right, that means this side is your sonic what you call subsonic flow, and the right hand side is your supersonic flow. But if I take a certain area ratio, let us say I am taking maybe 1.75 here, what it indicates? It cuts this area ratio to 1. That means, I can get this 2 Mach number. That means, for the same area ratio I will get 1 Mach number here, right, which is maybe around 0.4 kind of thing, the other one is around 2. What it says? I think I did not ask this question. If you go back and look at that equation, it will be having 2 solutions for the same area ratio, physically you can feel. And other thing is that if you look at your this temperature ratio and pressure ratio is changing, and for different specific ratio constant, that is gamma, it is different. With this I will stop over, and we will continue in the next class how we can use these equations and expression for talking about nozzles and other things.